We have seen how active and reactive power can be varied. Okay, also we have discussed regarding salient pole generators, whether the analysis or the control method that we have discussed for cylindrical rotor generators can be applied for salient pole generator also, that has been discussed, and also the synchronous motor. We have discussed about synchronous motors also, and how synchronous motors can be applied for uh, voltage control. Regarding the voltage control of synchronous generators, we have also discussed regarding the limit of overexcitation and limit of underexcitation. Now, what is left here? We have to discuss about two examples. Okay, numerical examples we shall be discussing, because this discussion will give you some better understanding regarding the theory of synchronous generators, particularly in connection with the operation of power system. Okay. Now you see that here we are considering a problem regarding a turbo generator. That means the cylindrical rotor generator used for thermal power stations. The problem is a turbo generator feeds 0.25 per unit power to infinite bus at 1 per unit. So turbo generator is feeding 0.25 per unit power. When we are talking about per unit power delivered by a turbo generator, then it is known to us that the power rating of the generator is the base power, because for per unit representation we need to define some base power and some base voltage. Okay, and so since we are discussing about a turbo generator, its rated voltage will be the base voltage, its rated power will be the base power. So 0.25 per unit power is being actually delivered by the generator to the sync to the power system, means it is delivering 25% of its capacity. Okay, to infinite bus means this is the power system, and there the voltage is 1 per unit, means there the voltage is equal to the rated voltage, rated terminal voltage of the generator. Okay, the excitation voltage is 1.5 per unit. What is the excitation voltage? Basically the generated voltage induced EMF, that is given to be 1.5 per unit. That means it indicates that the generator is overexcited. It is overexcited. 1.5 per unit is the generated voltage. That is also called the excitation voltage. That means voltage generated due to excitation of the machine. And the synchronous reactance 1 per unit. Synchronous reactance is 1 per unit. We know that steady state reactance of synchronous generator is represented by synchronous reactance. It is 1 per unit. You have to calculate the load angle, that means the delta, and the reactive power output of the generator. So at this operating condition, active power delivered is given, terminal voltage is given, induced EMF is given, reactance is given. You have to calculate the value of delta and the reactive power delivered by the machine. Easily this can be done. We shall see. Calculate the change in the active and reactive power output. See if number one is the turbine valve opening is increased corresponding to 100% increase in turbine torque. That means what we have to calculate, the change in the active and reactive power output of the generator when the turbine valve opening is increased. The valve opening is increased means obviously more steam is entering into the turbine, and how much is increased? Corresponding to 100% increase in turbine torque, such that turbine torque increases by 100%. Okay, keeping the excitation constant. So we don't vary the field current, only the input steam is increased by you increasing the opening of the steam valve. That means you can say that steam valve opening has been increased by 100%. Whatever was there, that much was increased. This is the meaning. So now there is a second condition, keeping the turbine valve opening fixed at the initial value, that means corresponding to the value when power generated was 0.25 per unit. Okay, the valve opening is again kept fixed at that value. Okay, such that the machine is generating 0.25 per unit power, the excitation is increased by 120%. Okay, and the excitation is now increased. Okay, it is 120%, 20%. Okay, now let us see how we can actually solve this problem. You see that what is given, it is 1 per unit is the terminal voltage Vt, it is 1 per unit EF, it is 1.5 per unit. These are very small script. Actually, I don't know whether how much you can see. Unfortunately, these are very small. Okay. Now, P is 0.25 per unit power. It is the power delivered by the generator, and synchronous reactance is 1 per unit. These are given. So you can use this relation that P equal to EF Vt by Xs sine of delta. P is given to be 0.25 per unit, EF is 1.5, Vt is 1, and Xs is 1. So sine delta you can calculate. Sine delta is 0.1667. Obviously, delta from here you can calculate. It is 9.6 degree. Okay, very simple. The given data very easily you can do. Now, from here, from this value of delta, you can now calculate reactive power generation. How much is the reactive power generation? It is EF Vt by Xs cosine delta minus Vt square by Xs. Okay, this is the relation. So EF Vt by Xs cosine delta, delta is 9.6. Put the value of Vt, put the value of EF, and it is 0.48 per unit. So when you see that generator is overexcited, as I told you, how? Because EF was 150%, okay, 1.5 per unit, and active power delivered is 0.25 per unit, but the reactive power delivered is 0.48 per unit. Obviously, the generator is overexcited. Now the changes. Torque control is applied. That means input power to the generator is increased. So obviously speed cannot increase immediately. So what happens? There is an increase in torque. So 100% is the increase of the valve opening. So what will happen if the 100% is increased? Means power input is increased by 100%. Previously it was 0.25 per unit. Now with the increase in opening of the steam valve, more steam will enter. As a result, P will become 0.5 per unit. How we came to this conclusion? Because we know that mechanical power input will be equal to electrical power output, since the generator is having no loss, because no loss is actually mentioned here. So that's why we may assume that there is no internal loss in the machine. So power input must be equal to power output. So P is 0.5 per unit. With P 0.5 per unit and EF not increased, remaining fixed at the previous value 1.5. Now what is delta? Delta you can again calculate from sine delta. Delta will be 19.5 degree. So because of increase in the input power, output power has increased. It has become double. How much is the corresponding increase in the delta value? It is around double. 9.6 was the previous value. Now it is 19.5 degree. Okay, it has also increased. You can say that almost in the same proportion, you can say. Okay, or you can say that we have mentioned that delta and P, they are strongly coupled. P and delta are strongly coupled. Here also we see that as P is increased, delta is increased, and there is a strong coupling between active power and delta. This discussion we have done in case of the power system, high voltage part of power system. You see that here, this is true for the generator as well. For the generator also, P and delta, they are very strongly coupled. Okay, P was increased by 100%, delta increases somewhat more than 100%, by more than 100%. Okay. Now, what is the corresponding increase in QG, reactive power? Reactive power, putting the values here, it is EF Vt by Xs cosine delta, new value of delta, minus Vt, it is 0.41 per unit. So what happened? Since field current has not been changed, only active power has been changed, there is an increase in the active power output, but at the same time there is a small reduction in the reactive power output from 0.48 per unit. There is a variation of Q, that is, it has become 0.41 per unit, so slightly reduced. How much is reduced? You find out the percentage reduction. It is 0.41 per unit from 0.48 per unit. So if we calculate the reduction with respect to the initial value was 0.48 per unit, it is 15%. So 100% increase in active power makes 15% reduction in the reactive power. 100%, around 100% increase in delta creates 100% increase in active power, but creates a very small variation in the reactive power. So again, here you can see that delta and Q, reactive power and phase angle, they are coupled but weakly coupled, not strongly coupled. Whereas you see that coupling between active power and delta, that is very strong, because for 100% increase in active power, variation in delta is somewhat more than 100%. So they are very strongly coupled. But if we see the coupling with reactive power, this is very weak, only 15%. Okay, so that is that analysis, that's property of power system, the decoupling property between reactive power and phase angle. Okay, that is established here also, and strong coupling between active power and delta, that is also established here in case of synchronous generator. Okay, now to come to the second part, excitation control when keeping the valve opening fixed. That means now the opening is corresponding to the 25% power output from the machine initial case. At this condition, it is EF is increased. Okay, it is made 120% of the initial value. Okay, so there is some actually error in the statement here. It was not by, increased to, it will be to 120%. Okay, so as the problem is treated, so it will be 120% of the initial value, so it becomes 1.8 per unit. You have not increased the active power input. This is a synchronous generator. Only the field current has been increased. Okay, so no change in active power output will occur because there is no change in the active power input. Generator basically is a converter. Mechanical power is being converted to electrical power. Okay, torque input we give, we are giving actually steam flow, increased steam flow containing more power. So accordingly, the output power is changed. Here, since we have maintained the input power constant, output cannot change, so there will be no change in the active power output. From the physical condition, we can come to this conclusion. So power remains fixed at 0.25 per unit, but field current changes, so excitation voltage or generated voltage changes to 1.8 per unit. So what happens to delta? Let us see. Vt remains 1 per unit because infinite bias voltage. Synchronous reactance remains 1 per unit. So what is delta? Delta, you see that it is 8 degree. That is again a slight variation. Previously it was 9.6 degree. Now it is 8 degree. So variation in field current causes a small variation in delta. We cannot say that it is completely decoupled. There is coupling, but again the coupling is weak. From 9.6 degree, it becomes 8 degree when the excitation is increased. Okay. Again, you see that we have seen in case of synchronous generator, if you increase the excitation, what happens? Delta decreases. Increases excitation, previous 0.15 to 1.8 per unit, delta has reduced. Okay, more you increase the excitation field current, so more the value of delta will decrease. Okay, so with this reduced value of delta, how much is the reactive power? You see that now reactive power variation is very high. It is 0.78 per unit. EF Vt by xs cosine delta, delta is 8 degree now, minus Vt square by xs. Okay, it is 0.78. Initially, it was 0.48 per unit. From 48 per unit, because of the variation in field current, okay, because of the variation in field current, how much the field current has increased? It is 20% increase in field current. Now, the reactive power varied from 0.48 per unit to 0.78 per unit. How much is the percentage variation? Is 63%. So there is a very strong coupling. You see that between the field current of the generator, excitation of the generator, and the reactive power variation of the generator. Okay, so again, this example, basically this computation, the method that you will be following, these are very simple, but it is very instructive in the sense that here also we can establish those relations in power system. That means the strong coupling between the active power and delta, weak coupling between reactive power and delta, strong coupling between excitation voltage, that means the field current and reactive power, and weak coupling or no coupling, you say, between field current and active power. Okay. So this is established, and this was the purpose of actually showing or discussing this problem here. So is it clear to you, all of you, this problem? Could you understand, or any doubt you are having? You can please tell me if you are having any doubt. বুঝতে পেরেছো সবাই?
Yes, sir.
Okay. Now the second problem that is not the solution is not given here. I shall discuss the solution. You will be doing this problem yourself. Okay. A 13.8 kilovolt 100 MVA 50 hertz synchronous generator delivers a load of 75 MVA at 0.9 power factor lagging to an infinite bus held at 1 per unit. Okay, this is the first line. So rating is given 113.8 kilovolt, 100 MVA is the MVA rating of the machine. Rated frequency is 50 hertz. It is delivering 75 MVA at 0.9 power factor lagging. So you can find out how much is the active power, how much is the reactive power. Okay, and it is because the power factor is given, and it is delivering power to infinite bus held at 1 point. That means power system voltage. Obviously, the power system voltage is the terminal voltage of the generator. That is 1 per unit. Means 13.8 kilovolt is the terminal voltage. Okay, because the per unit quantity, when we are actually referring a machine and discussing everything in terms of this machine, then this per unit quantity is defined on the basis of the base voltage and base power of this machine. So base power voltage of this machine is 13.8 kilovolt. This is the rated voltage. So this is the 1 per unit voltage, means this rated voltage of the machine, terminal voltage of the machine. Now calculate the active and reactive power. If the minimum excitation EMF increased by 10%, no, it's not. That again, minimum will not be here. If the excitation EMF is increased by 10%, so this minimum, this will not be actually here. So I shall actually correct it. When I shall be sending you this, perhaps I have already mailed you this content. So there this correction is needed. So I shall see whether I can edit it. If I can edit it, I shall eliminate this minimum. Minimum will not be here. Okay, increased by 10%. So when the excitation is increased by 10%, how much is the active and reactive power? You have to calculate. You can do it very simple. What is important and why this problem is actually discussed here, being discussed here, you have to determine also the minimum excitation EMF expressed as a percentage of the initial value below which the machine would fall out of step. We know that we can reduce the field current of the generator. How much we can reduce the field current? That is decided by the stability of the synchronous generator, and that stability, rather it is called the angle stability, that is decided by the delta equal to 90 degree. That means the steady state stability limit of the generator. Cylindrical rotor type generator, it is 90 degree. So delta will be 90 degree. Under that condition, what will be the value of excitation? That is the minimum excitation that you have to determine. and you have to assume that synchronous reactance is 40%. 40% means 0.4 per unit. You know that this is how we can express. I sometimes we can represent it in percent, sometimes we can represent in per unit. Okay, and mechanical input to be constant. So mechanical input power is kept constant. That means keeping the active power constant, we should reduce the field current. Machine will be under excited. You have to determine what is the minimum value of this excitation. That means you will be determining the value of EF corresponding to delta equal to 90 degrees. So that is how this problem is solved. So you see what was the initial value of EF that you can calculate from the first part, and what is the final value of EF after the reduction in field current, so that you can calculate. So you can actually then calculate the what is the minimum excitation value permissible for this patient. So I hope that now this problem you can easily solve. Okay, if anybody of you are having any doubt regarding how to solve the problem, then you may discuss, you may make any question, any doubt if you are having. If not, then I shall be proceeding to the next topic. That means the synchronous generator. Discussion on synchronous generator is finished here. Okay, particularly it is not finished, you can say. How much will be needed for our purpose when we are discussing the frequency control, that much is done here. Okay, next we shall proceed to frequency control. Okay, now let me know whether you will be in a position to solve this problem or not, or you are having any doubt regarding the solution of this problem. Solution I have not given here, you will be doing it. See whether you will be in a position to solve it or not. Bolo. Is it clear?
Yes.
Okay. Then I shall be moving to the next part. Okay. And next part is regarding the frequency control. Frequency control. Okay. Okay. So we have seen that how to control the frequency of power system basically by controlling the active power generation of the generator. How to control the voltage by controlling the excitation of the generator. And sorry, the active power control is by controlling the, or field current control, frequency control is by controlling the input to the generator. That means the active power generation or turbine torque input, and voltage control is by, or reactive power control is by controlling the excitation of the generator. That means the DC field current of the generator. Now that is schematically shown here in a compressed approach. Here we are showing that schematically. Is there anybody coming to join at this time? Okay, after half an hour. All right. Is this portion. Okay. Now this is schematic diagram of the frequency and voltage control. You see that here as if this box is showing us the generator. Okay, that means the synchronous generator. Generator is having the field winding, it is shown here, and field winding will be supplied by direct current from a DC source. And for the control of the field current, there is one excitation controller, field current variation. That is, field current also is called the excitation, and the varying that current will be done by using some controller. That is the excitation controller here. And this is the shaft of the generator. Shaft of the generator is coupled with the shaft of the turbine here. Steam turbine is here. For the steam turbine, this is showing the passage from the boiler to turbine, and there is opening of the steam valve is shown here. That means how much steam will enter into the turbine. That will be controlled by controlling the opening of the steam valve. It will be increased, it will be reduced depending upon the requirement, and that steam valve is shown here. How the steam valve will be controlled? By a steam valve controller. And how the steam valve controller will be acting? It will be measuring the frequency of the voltage or the speed of the generator. So these are the three-phase output of the generator, showing that P plus JQ is the power delivered by the generator to the power system. So that means the system voltage you can measure from here. So you can either measure the frequency of the generated voltage, or you can measure the frequency of the rotor. So that means the speed of rotation of the rotor. Sometimes speed will be measured, sometimes the frequency will be measured. All the same, either you can measure the frequency or you can measure the speed of rotation for the machine. Okay, so it will be measured, and that frequency will be compared with the reference frequency. What's the reference frequency? This is the declared frequency or the rated frequency of the system. At what frequency you will be operating the system? That is the declared frequency or the specified frequency of the system. So this frequency will be compared with the reference frequency. Okay, if there is any deviation from the reference, it may increase, it may decrease. If there is any deviation, then it will be, you are comparing these two, and accordingly opening of the steam valve is being controlled. Either it will be increased whenever the frequency is found to be less than reference, or it will be reduced when the frequency is found to be more than the reference frequency. So this is how the frequency controller will act. The frequency will be measured, it will be compared with the reference frequency. Any error will be actually used to control the opening of the steam valve of the turbine. Steam valve of the turbine, if it is increased, more steam will enter. If it is reduced, steam flow will be reduced here, and as a result, the turbine either will be rotated or turbine torque will be increased or decreased, and turbine shaft is coupled with the generator shaft. So as the turbine power output is changed, obviously the generator input, mechanical power input to the generator is also changed. So this is the mechanism of controlling the input to the generator and controlling the frequency of the generator. And how the voltage is controlled? By controlling the field current. How the field current will be controlled? Again, the terminal voltage will be measured here. This terminal voltage will be compared with the reference value. What is the reference value? Reference value is the declared terminal voltage of the machine. So that is the reference. At what value we shall maintain the voltage? That will be declared value, and that is the reference value. So measured voltage will be compared with that result, that reference value, and if it is found to be less, field current will be increased. If it is found to be more, then field current will be reduced. Okay, so here the voltage sensor and comparator, it will finally actually regulate the field current of the generator, and it will then instruct the excitation controller. Excitation controller accordingly will change the excitation current or field current of the generator, and as a result, the generated voltage will be changed. So this is how the frequency control and voltage control will be performed in a for a synchronous generator. Now, you see here, can you tell me what will be the time constant of the excitation control expected value? Okay, how large, how small, and what may be the time constant of this frequency control? Which one will be faster? Frequency control will be faster, or frequency control will be faster, or excitation control will be faster? What is your impression? What is your idea about that? These are the two functions. Frequency control here in this part, and here in this part, voltage is controlled, excitation is controlled. Now, which control, voltage or frequency, is faster, and which is slower? Can anybody tell me? Can anybody answer? Anybody guess anything regarding the speed of frequency control and speed of voltage control? Who will determine the speed of frequency control or the speed of the voltage control?
So frequency
Anybody?
control.
Time constant.
Excitation control will be fast, I think.
Excitation control will be faster and frequency control will be slower. Why? What is the reason?
Because frequency control means the opening of valve or closing the valve. This is a mechanical thing, but excitation control means the uh, field excitation. That means the more current or less current. But current control is more easy than the, I think, mechanical things, is opening of valve or closing of.
Okay, yes. Basically, what will happen? Excitation control will be much faster than the frequency control. Why frequency control is slow? You see that frequency control involves the rotation. That means it involves the inertia of the generator. Inertia means how much is the mass of the generator rotor. Not only the generator rotor, that includes the generator rotor along with the turbine. So it requires opening of the steam valve, closing of the steam, reducing or increasing the opening of the steam valve. A large force is needed. So application measuring sensing that the frequency has changed. Changing the frequency itself will require some time because of the inertia involved. And then you have to sense the frequency change. Then you have to control the opening of the steam valve. That also will require time. So you see that frequency control rather is a slow process because of the inertia is involved here. Inertia of the valve control process, inertia of the frequency change process. Okay, so it will require much more time. And how much is the maybe the how maybe the speed of the voltage control? Voltage control, you see that it's control of field current. Control of field current. So we shall have to see what is the source that supplies the field current to the generator. This is a DC source. In older machines, the DC source basically were the sources basically were the DC generators. Okay, you can use a DC generator, no problem. But problem is that DC generator, that is actually somewhat problematic. Why problematic? Because that is the commutator is there, it will be involving some problem. Whenever commutator is there, then there will be the problem of sparking. So that's why that DC generator, at the same time, this is somewhat slow also, because if you want to change the field current, how we can do? You have to change the DC generator. So for either you can change the DC generator voltage. How? Then you have to change the excitation of the DC generator again. So this is a lengthy process. So that is somewhat time consuming. Obviously, still then is that is faster than the frequency control. But in modern generators, not modern generator means for the last few decades, you can say the this method of frequency voltage control is not being applied. That means DC generators are no longer in use for supplying current to the field winding of the generator of the alternator. Okay. Rather, what is done? In some cases, AC generator will be utilized and AC generator output will be rectified through controlled rectifier. Controlled rectifier means basically thyristor driven rectifier. Okay. Or sometimes what is done, the generator output, alternator output itself is actually rectified and given as input to the field winding. So if the AC generator output is rectified or the generator becomes self-excited, in that case, what will happen? You have to control the rectifier only. And how you can control the rectifier to control the field current? Basically by increasing the conduction period or decreasing the conduction period of the thyristor. And increasing and decreasing the conduction period of breathing, you have to control. That means that you are increasing the conduction period or decreasing the conduction period. That will be completed by half a cycle only, because in each cycle, every half cycle you have to apply that control. So you see that what is the speed? Speed is the response time is of the order of half a cycle only, and half a cycle means how much is the time? For 50 hertz frequency, cycle time is 20 millisecond. Then half cycle time is 10 millisecond only. Okay, that means within 10 millisecond, your control will be applied. That means you see that whenever you are changing the field current, automatically field current will change the field flux, as that induced voltage will change. So you are not concerning with the speed of the generator here. Basically, the field current change, field flux change, that is being used. So this is very, very fast, much faster compared to the speed of the frequency control. Now, how we can utilize this difference in the speed of the two control loop? There is one control loop is the for the voltage control, the second control loop is for the frequency control. You see that whenever you are applying any field current control, changing the field current, so you see that it is so fast that you can assume that with respect to that speed, as if the speed of the or frequency of the machine is almost constant. You can assume that because before any change in the frequency takes place, your field control, field current control will be finished. Similarly, if you talk about the frequency control, it is rather slow. So slow is that within that time, if you control the frequency, that you control the voltage, frequency voltage control will be finished very early. So you can say that as if this control, that means the control of frequency and control of voltage, we may say that these two are totally independent process. That means frequency control does not have any impact on the voltage control, and voltage control also does not have any impact on the frequency control. Why we can actually assume so? Because this is too fast. So it is so fast that we can assume that frequency is almost constant with respect to the speed of voltage control. Similarly, we can assume that the transient or the dynamics of this part is so slow that with respect to this time constant, we may assume that the field current control is almost instantaneous, so that it will have no impact on the frequency control. That's why while discussing the frequency control, we shall assume that we need not at all consider or we need not give any attention to the voltage control process. Voltage control as if is not done, or if it is done, it is done instantaneously. We need not think about that. That means we shall assume that we need not bother regarding the voltage of the generator. Okay, as if that is constant with respect to the frequency control, we may assume the generator is being operated at constant voltage, and therefore there is no as if no change in the excitation at all. That we may assume. Why we can assume this? Because that is so fast that any changes here is will be taking negligible time with respect to the time constant of the frequency control. Am I clear? Could you get the point? That means while discussing the frequency control that we shall do now, we shall disregard any variation in the voltage of the synchronous generator. We shall assume that that voltage is constant. Actually, if that voltage is not constant, the control of the voltage is so fast that it will, you can see that with respect to the control of the frequency, that voltage control is so fast that we can say that if it changes, it may be corrected instantaneously. So we need not bother about the variation in the generator terminal voltage while we are discussing the frequency control. Okay, is it clear? Could you get
Yes,
the
sir.
point? All right. বুঝতে পেরেছো? Or do you need further discussion? বলো।
না স্যার ঠিক আছে।
ঠিক আছে, that means we can actually assume that frequency control is independent of voltage control, and when I shall be discussing voltage control, then also we shall assume voltage control is independent of the frequency control because of the speed difference between the two processes are very, very large. That's why. Okay, now let us come to the frequency control. Okay, The frequency control is implemented through speed governing mechanisms, speed governor. Okay, and this is the schematic diagram of the speed governing mechanism of the synchronous generator. Okay, this is a simplified functional diagram of primary ALFC. ALFC means basically you can say that it is the automatic load frequency control. ALFC indicates automatic load frequency control. Why it is automatic? That will be clear after some time. Okay, that then you should be first discussing this, then you should see why it is called automatic. It is called load frequency control. Why? Frequency control is understood, but why this load frequency? Because basically frequency control is affected by varying the generator output, and generator output has to be varied when there is a variation in the load demand. That's why actually we are controlling the power supply to the load. Okay, because frequency variation is due to the variation in the power demand, and the mismatch between the power demand and power generation is the sole reason for frequency variation. So when we shall be controlling the frequency, we are controlling that in response to the variation in load. That's why it is called the load frequency control. Okay, and why automatic? That will be obvious. That will be clear to you after I discuss this whole thing. Okay, now let us discuss the components involved in the frequency control. What are the components involved? This is a mechanism. The arrangement is shown here. This is a speed governing mechanism. We say this is the speed governing mechanism. And what are involved in this speed governing mechanism? Obviously, this is a schematic diagram, and actual implementation will vary depending upon the you can say that manufacturer. Okay, who are implementing this. Now you see that here the speed governing mechanism is operation is actually basically controlled by this the so-called speed governor. Okay, speed governor basically its function is to govern to regulate the speed of the synchronous generator. Now what this speed governor is having, it is having two fly balls, one here, another here. These are the two fly balls. Okay, that's why this is called the fly ball speed governor. Sometimes these two fly balls are connected with the help of a spring. Okay, so this is a rigid link. This is also a rigid link, and from this pivot, this is a rigid link. This is a rigid link. This is rigid link. This is rigid link. So there are four rods, you can say. Okay, and another, this is again, this is rigid link. So it is pivoted here. It is pivoted here. These fly balls, okay, they are so arranged that they will be rotating along with the rotor of the synchronous generator. Okay, that means that means they are somehow coupled with the rotor of the synchronous generator, rotor of the generator. That means when the generator is rotating at synchronous speed, there will be a certain tension on the spring, because the fly balls also will be rotating at synchronous speed. So there will be certain tension on the spring. If the generator rotates at a lower speed, what will happen? Then fly balls also will be rotating at a lower speed, less than the synchronous speed. So if the speed is lower, means centrifugal force will be lower, so the balls will be coming closer, or tension on the spring will be somewhat less than the tension corresponding to the synchronous speed. Similarly, when the speed is above synchronous, the balls also will be rotating above synchronous speed. As a result, there will be more tension because centrifugal force will increase. So this ball will be moving in this direction, this ball will be moving in this direction. As a result, there will be more tension on the spring. So what is the tension on the spring? That will be decided obviously by the speed of rotation of the fly balls. And who decides the speed of rotation of the fly balls? It is the speed of the rotation of the synchronous generator. Okay, that means basically speed of the rotation of the synchronous generator decides the frequency of generation. That means when the frequency of generation is more, then there will be more tension on the fly balls. So fly balls will be moving away from each other. When the frequency of generation is less than the synchronous speed, then the fly balls will be coming closer because the tension will be less on the spring, because the fly balls are also rotating at a speed less than the synchronous. When the speed is synchronous, then there will be a predetermined or predefined tension on the spring. So there will be a distance between the two balls and specified tension on the string. Tension below that will indicate low speed, tension above that will indicate high speed. Now, again, this is a rigid link. This is a one rigid link. ABC is a rigid link. CDE again is a rigid link. Okay. This is rigid link. This is also rigid link. Okay. Now you see that, say somehow if this position C is fixed, then what will happen? We shall discuss regarding how we'll decide the control the position of the C. So as the fly balls are moving at a speed higher than synchronous, then what will happen? They will go away from each other. There will be increased outward force, increased tension on the spring. As a result, B will be pulled down because they are moving in this direction. Is moving in this direction. This is a rigid link. So what? How these balls can move apart? Obviously, by pulling B downward. Okay, is it clear? Similarly, when the tension on the spring is less than the specified value, specified value means tension corresponding to the synchronous speed. When the tension is less, then what will happen? These two balls will come closer, and how they may come closer? This length obviously cannot be reduced. So they are coming closer, I mean they will be pushing B upward. So at the speed of the five balls, it is above synchronous, B will be moved down. When it is less than synchronous, B will be moved up. Okay, that means movement of B will be controlled by the speed of the synchronous generator. How? Because speed of the generator will dictate the speed of the fly balls, and as a result, at speed above synchronous, B will be moved down. At speed below synchronous, B will be moved up by the action of the fly balls, by the action of the fly ball speed governor. And this is the heart of this total frequency control mechanism. Okay. Now, this is called a speed changer. This arrangement is called a speed changer. What is the function of the speed changer? By this speed changer, can give a power increase command to the governor, to the speed governor, or a power decrease command. So when you actually give a power increase command, you will be give a raise signal, raise power. How? By moving the speed changer downward. If you move this position downward, then you will be actually giving a power increase command. How we are giving a power increase command, we shall explain. And when you are lowering the, we will be giving a decrease power command, that will lower the power output. That will be given by raising the position of the speed changer. So you move the speed changer position upward, you will be giving a command for decreasing the power output of the generator. Whenever you are pushing the speed changer position downwards, you are giving a power increase command. How this power increase or decrease command is working, that I shall explain. Now ABC, as I told you, is a rigid link, pivoted at B, and similarly CDE is again a rigid link, it is pivoted at D. Okay, now there are two cylinders. You see that these two cylinders consist of, it consists of two cylinders, and this is basically called the hydraulic amplifier. Hydraulic amplifier. Basically, you see that here will be there will be high pressure oil kept, and the purpose of this hydraulic amplifier actually will be to increase or basically open or increase or decrease the opening of the steam valve. So you are giving some or increase command or decrease command. So you are changing the position of the speed changer. As a result, you will be changing the opening of the steam valve. So for affecting the opening or closing of the steam valve, a high force, large force has to be applied. There's force magnification will be affected by this amplifier. That's why it is called the hydraulic amplifier, this arrangement. Okay. This hydraulic amplifier has actually this piston, it is called the main piston, and here there are two valves, these are called the main valves. So it is a small narrow cylinder and there is a larger cylinder here. Okay, this cylinder and this cylinder, they are filled with oil, and this is connected with a high pressure oil pump. So that oil pump will maintain the oil pressure here at a high value. That means always it will be kept at high pressure. Okay, the oil pump is connected here. This main piston is again connected with this rod, and this rod is a schematic diagram. Basically, it is actually being used here to either increase the opening or decrease the opening of the steam valve, as if this is showing the passage of the steam from the boiler to turbine. Okay, this is the passage from boiler to turbine. Boiler is here, steam is generated. This is the opening of the steam valve. Basically, this is the steam valve position. If you move this off, main piston off, then the valve opening will be reduced. If you move it down, valve opening will be increased. Okay, so close the steam valve somewhat means you give a move this piston upward. If you increase the opening, move the piston downward. Okay, so basically, again I am describing what is there. We are showing the steam valve. That means steam valve is in the passage between the boiler and the turbine. Steam valve opening and decreasing or increasing the opening of the steam valve is done by means of this main piston. When the main piston moves up, steam valve opening will be reduced. When the main piston moves down, steam valve opening will be increased. Now, in the along with this main piston rod, we have a rigid link CDE. Okay, pivoted at D. Here it is connected with the main piston rod at E. Another rigid link is there, ABC, pivoted at B. Okay, this at B, we have this rod connected to the speed governor mechanism. Okay, speed governing mechanism, and the speed governing mechanism is the heart of this total frequency control process. The speed changer is here. The speed changer is used to give any power increase command or power decrease command, because after basically for controlling the frequency, either you have to increase the speed, increase the power output, or decrease the power output of the generator, and that command also can be given externally. Okay, and that can be given by either increasing or decreasing the position, lowering or raising the position of the speed changer. Okay, is it clear? The description is clear. So assume that any downward direction we shall assume to be positive. Here it is written delta xd. Xd gives you the position of this point D, and delta xd indicates the change in the position of xd, position of D. X indicates the position. Okay, position is measured by x xd, and how much is the position is changed, that is given by delta xd, and a downward direction of D is considered to be positive. Similarly, xc represents the position of C. Delta xc represents the change in the position of C. Again, a downward direction of C gives a is considered to be positive. Similarly, for B, position is measured by xb. Change in the position of B is measured by delta xb. Again, a downward direction of xb is considered to be positive. Position of A is measured by xa. Change in the position delta xa, and downward direction again considered to be positive. Everywhere the downward direction is positive, upward direction is considered to be negative movement. Okay. All right. Similarly for E also, delta xc is the change in the position of E. Okay. Now let us see how this this governing mechanism actually works. Let us assume that The power system is operating at a steady state at the declared frequency. Okay, say the power output for the generator is known. It is a steady state power. At steady state, a certain amount of power is being delivered by the generator. Okay, and the generator is operating at synchronous speed. Since the generator is operating at synchronous speed, its frequency is synchronous, and at that frequency, B is at a predetermined value, predefined value. That means when the speed is synchronous, B always will lie at that point. Okay, B will be there. If the speed is synchronous, B will be at its predetermined position. Okay. Now, since the speed is synchronous, fly balls are rotating at synchronous speed. That's why B is having its predetermined position. So fly balls are rotating at a predetermined speed corresponding to synchronous speed. There is the predefined tension on the spring because the speed is synchronous. Now let us give a power increase command. Say for some reason we want that the speed of the power output of the generator will increase. If we can change the power output of the generator, then we can actually control the frequency also. Because for frequency control, power output of the generator has to be changed. So let us see how power output may be increased or power output may be decreased. For the first attempt, let us assume that we want to increase the power output of the generator. So what we shall do? We shall give a power increase command or raise power output command by lowering the position of the speed changer. Already we have mentioned that for increasing and decreasing the power output, you may give a command to the speed changer. So you have to push the speed changer position downward. That will give a raise power command. That means the power, increase the power output. This command is given. What will be happening after it is pushed downward? You see that this piston, main piston, it is having an opening here, it is having an opening here, it is filled with high pressure oil, it is also filled with oil, and this cylinder is finally connected with the high pressure oil pump. That oil pump is maintaining its pressure always. So what will happen? Since there is a steady state, that means obviously there will not be any oil movement, because if any oil movement is there, then main piston cannot be at a fixed position. Main piston is at a fixed position means opening of the steam valve is at a predetermined position. It is have a definite value. Means there is no movement of the oil, because if there is any movement of oil, then main piston also position also will be moved, because oil will be moving out or moving in. As a result, there will be more thrust on the main piston or less thrust on the main piston, and main piston position will be changed because there will be draining out of oil, or oil will be entering here. So what is happening? That is not happening, because steady state means everything is steady. Everything is at the steady state position. So opening of the steam valve is steady state. At steady state, there is no oil movement. There is no oil movement means this opening here is totally closed by this pilot valve, and this opening also is closed by the pilot valve. And these pilot valves, what we call these pilot valves, these valves are so designed that at steady state, this opening will be closed and this opening will be closed. That means there will be no shifting of oil from one cylinder to another, or from the oil pump to the cylinder. There will be no change in the oil movement, but the pressure will be kept fixed by the oil pump. Okay. So what is happening? Oil is at its predetermined value. That means there is no oil movement. The opening of the steam valve is at a certain position. So E is fixed, means D also will be fixed at its previous value. C also will be fixed at a previous value. And since there is no change here, you cannot change C directly now. Okay. So what happened? Now you have given a power increase command. You have lowered the position of the speed changer position. So it has pushed down. You have pushed it down. As you have pushed it down, there was some speed of rotation corresponding to synchronous speed. Okay. So what is happening? So if you have moved it down, what will happen? Obviously, you cannot change the position of B, because position of B will be determined by the speed of the fly balls. And the speed of the fly balls will be determined by the speed of the generator, which is synchronous. Means tension on the spring is corresponding to synchronous speed. Means position of the B you cannot change. It is being determined by the frequency of the generator. So what will be happening? Now what will be happening? A is moving down because of the push you have given. So as A is moved down, B will remain fixed. So obviously you are giving some pressure here. As you are giving that pressure, but that pressure will not be sufficient to change the position of B. Okay, because it is solely determined by the tension of this thing. So C has to move up somewhat. C will be moving up somewhat. As C will be moving up, okay, it is moving down, C will be moving up. So C will be moving up means this is also fixed. It's because was no oil movement. So unless there is any oil movement, you cannot change this position. So but you have given a push here. So as a result, C will be moved up. So as C is moving up, along with C, D will be also moving up somewhat. As D has moved up, what will happen? An opening will be created here. Small opening will be created here. Similarly, this piston also, this valve, pilot valve also will be moving up. So an opening will be created here. So an opening here in the lower portion of this valve, an opening here in the lower portion of the valve. As a result, what will happen? Because of, and since the high pressure oil is kept at high pressure here, there will be thrust on the oil here. So through this opening, there will be a thrust applied by the high pressure oil pump to this cylinder. And through this opening, since there is oil and opening here, oil will come out through this opening and oil will enter through to this chamber through this opening. As a result, there will be a pressure applied on the main piston will come down. Okay, so main piston will move down, oil is coming out from this opening, through this opening, oil is entering through this opening, main piston will come down. As the main piston is coming down, what will happening? Main piston is coming down means you see that there will be some increased opening, because opening will be increased if it comes down. So increased opening of the steam valve. That means more steam now will enter into the turbine. As more steam is entering into the turbine, it is equivalent to applying more mechanical power input to the generator. So generator speed now will increase because generator delta output cannot increase immediately. So generator speed will increase. Could you get the point? So with the power increase command given here, A will be moving down, B will be fixed at its initial value, initial position, C will be moving up, along with C, D also will move up. As D is moving on, an opening will be created here in the lower portion of this, below this pilot valve. Again, this will move up, so opening will be created here also. Through this opening, oil will come out from this chamber. Through this opening here, high pressure will enter to this chamber. As a result, the main piston will move down. As the main piston is moving down, opening of the steam valve will increase. As opening of the steam valve is increased, there will be more steam entering into the turbine. Means turbine torque is increased. As turbine torque is increased, now speed of the generator will increase. With the speed of the generator increased, what will happen now? The delta will increase, so accordingly the delta power output of the generator also will increase. Okay, so is it clear? Now something more, some more thing will happen that I will explain. But is this part clear? What I have said up to
Yes,
now,
sir.
until now? Okay, is it clear?
স্যার বলছি ই যদি মুভ ডাউন করে তাহলে তো ডিও নিচের দিকে মুভ।
হ্যাঁ, কোনটা?
স্যার একদম লাস্টে যদি ইটা নিচের দিকে মুভ করে তাহলে তো ডিও নিচের দিকে মুভ করে, দিয়ে তো
হ্যাঁ,
ভালভটা আবার ক্লোজ হয়ে যাবে।
মুভ করে, কিন্তু কি হয়েছে এখানে, যেই নিচের দিকে মুভ করতে থাকবে, তখন তার পরেরটা আমরা হ্যাঁ সেই পজিশনটা আমি এখনো বলিনি, যে মুভ করবে, মুভ করার পরে কি হবে সেই পোর্শনটা এখনো বলিনি, আই শ্যাল ডিসকাস দ্যাট নাও। ওকে, এটা মুভ করার সঙ্গে সঙ্গে কি হবে, there will be more steam entering into the turbine. As a result, কি হবে, there will be more power input to the generator. So more power input to the generator means generator speed increases. What will happen after that, I shall now discuss. So it was previously কি হচ্ছিল, it was previously moved up. As a result, D also moved up. এইবার E যখন নিচের দিকে নামলো তাহলে D কিছুটা নামবে কিন্তু ওই আগের পজিশনে ফিরে আসবে না, কাজে ওপেনিংটা এখানকার ওপেনিংটা একটু চেঞ্জ হবে, but it will not be completely closed. Okay, so what will happen after that I shall explain, but now tell me whether this much is clear to you or not. Well, is it clear to you up to this stage?
Yes.
Okay, now the opening of the steam valve has increased, but what happened, but still there is some opening here, there is some opening here, but that means oil flow continues. Okay, and this is moving down. Okay, so as a result of increased steam, speed of the generator will increase. As a result, delta will increase, so there will be more power output. But this will not, steady state has not yet been established. Power output বেড়েছে কিন্তু steady state reach করেনি। কিভাবে steady state reach করবে? Steady state reach করতে হবে at increased power output condition. Then only the generator will remain at stable condition. Now what happens? If the opening of the steam valve increases, then speed of the generator increases. As speed of the generator increases, what happens? So the fly balls are coupled with the rotor of the generator. So fly balls are also now rotating at a speed higher than the synchronous speed, because generator rotor is rotating at a speed above synchronous. So since generator rotor is rotating at a speed above synchronous, previously what happened? B has moved up. No, B did not move up. B was at the previous value. Okay, now there is increased speed of the generator rotor. So as the speed is above synchronous, so fly balls also will be moving, rotating at a speed above synchronous. There will be more tension on the fly ball. As a result, what will happen? Now you have previously given a power increase command. That means as if you have moved A from one position to another. You have moved A from a previous position to a lower position, and A is kept there at that position. A is now fixed. Now B was at its initial position. So what happened now? Since the generator is rotating at a speed above synchronous, fly balls also are rotating at a speed above synchronous. The tension on the spring will increase. As a result, B will come down from its synchronous speed position. B will come down. As B is coming down, A cannot move down any further because A is been kept fixed at the new position. So B is coming down means it cannot come down unless C is also coming down. So along with B, C also will be coming down. You see that previously C had moved up. Now what B is doing, as B is moving downward, C also is being moved down. Along with B, C moves downward. So as C is moved downward, D also will be moving downward. Okay, D also will be moving downward. So, and since D is moving downward, so there will be an attempt for reducing this opening. So this process will go on. Sometimes it will move up, sometimes it will move down, because any change obviously will not be some oscillation free. So there will be some oscillation. Sometimes it will be open somewhat, sometimes it will reduce somewhat. So finally, when the new steady state is established, you'll see that again this opening will be closed, this opening will be closed, and C will be actually, because of the increased opening was there. So the speed is above synchronous. So what is happening? At above synchronous speed, B has moved down, C also had moved down, D also has moved down. So it will be somewhat reduced. So in this way, that means as an effect of the downward movement of the speed changer position, what we have done, you see that opening of the steam valve has increased, and after the opening of the steam valve has increased, now there are processes by which again these opening are getting reduced. But in the meantime, as the speed again has increased, what will happen? Delta will increase. As delta has increased, so power output will increase. As the power output increases, then we have discussed previously regarding the when we have discussed the oscillation of the synchronous generator. You have seen that again there will be some variation in the speed of the synchronous generator from above synchronous. The speed will come down. It will below it will be equal to synchronous speed. Then again it will be below synchronous speed. That means again there will be some movement of B depending upon the speed of rotation of the these fly balls. Okay, that means only let us now focus on the initial oscillations only. Initially, after giving a power increase command by lowering the position of A, okay, what happened? Opening of the steam valve has increased. As a result, what happened? Generator started rotating at the speed above synchronous. So more steam entered, power output has increased, and in this process again there was some change in the position of this pilot valve and the main piston. And when everything becomes stable finally, it may be said that finally again at steady state what will happen? Power output will become, it will be increased power output corresponding to the given power increase command. But finally when the steady state is reached, this position of the pilot valve has to be at this position such that there is no oil movement between these two chambers. So at the new steady state, what will be happening? The increased position of the steam valve will be there. Okay, but the main this opening will be closed. This opening will be closed means a new steady state will be arrived, and then again the generator will be rotating at synchronous speed. So what will be happening? Because of the power increase command given here, opening of the steam valve will be increased, and then between these transitions of the position of B, C, all these things will happen, and they will be changing their position until a new steady state is arrived, and that new steady state means again the generator is rotating at synchronous speed. Am I clear to this?
Yes, sir. Yes.
Now you see that we have given a power increase command only. Nothing else is being done from outside. From outside, what you have done? Simply you have changed the position of A. And whatever has happened after that, that has happened because of the action of the fly balls, because of the action of the hydraulic amplifier, because of the movement of this main piston, movement of this pilot valve, and everything has happened automatically. The arrangement is such that you need not do any extra arrangement, any control, any further control is not needed from outside. What is needed? Simply you will be either giving a power increase command or a power decrease command. Okay, when you give a power increase command, power increases ultimately by increasing the opening of the steam valve, and that is being done automatically by this mechanism, which is called the speed governing mechanism. That's why it is called the automatic load frequency controller, automatic load frequency control loop, or automatic load frequency controller. This is how it is operating. Now, when you give a power decrease command, the opposite thing will happen. Give a power decrease command, say by give a decrease power command or lower power command. So you'll be moving the speed changer position upward. Say initially generator was rotating at synchronous speed. Okay, so B was at a predetermined position, but you have given a power increase command. The movement of oil was not there. This position is fixed. Here it is closed at steady state. Also, it is closed at steady state. Remember that steady state means there will not be any movement of oil in the hydraulic amplifier, and this opening and this opening, both the openings will be closed by the uh, pilot valve, and main piston also will be fixed at a position. Okay, now system is operating at steady state, frequency is normal, and now you have given a power decrease command. How? You have moved the speed changer position upward. So speed changer has some definite few steps. From one step, you have increased the, you have raised the position of A upward. It's one step upward, you have moved it. And as you have moved it, it will remain fixed at that position. It will not be changing automatically. Unless you change it, nobody can change it. Okay, so A will be moved, A has moved up and it is fixed at that position. Now, tension on the spring is corresponding to synchronous speed. So when you have moved A up, how for for actually pushing B upward, obviously C have to move downward, otherwise it cannot go up because this is a rigid link and figurated B. So when you move A upward, C has to move downward. When C is moving downward, initially this was closed, this was closed. That means the pilot valves were just at this position, this valve was just at this position, means now as C is A has moved up, means C will be moving down. As C is moving down, D also will be moving down. Okay, as D is moved down, what will happen? An opening will be created here at the upper position of the pilot valve. An opening will be created here at the upper position of this valve. Okay, so here what is happening? Sorry, it has moved down, opening will be here. It has moved down, opening will be here. Now high pressure oil is connected here. This high pressure oil now will try to push high pressure oil through this opening in this chamber. Now there is an opening here. So as a thrust is given towards the lower part, and upward thrust is given to the main piston will move up and excess oil from this chamber will drain out through this opening. Okay, excess oil will be draining out through this opening. So because of the high pressure given by this oil pump, so an upward thrust will be given here. So main piston will be moving up. As the main piston is moving up, means obviously opening of the steam valve will be somewhat reduced. Okay, as the opening of the steam valve is reduced, what will be happening? There will be less steam entering into the turbine. So as if you have reduced the mechanical power input given to the generator. As the power input decreases, what will happen? Power output remains fixed at its previous value because delta has not changed immediately. So there is more power output than power input. What will happen? Speed of the generator will decrease now because power input has decreased, speed of the generator will decrease from synchronous valve. As the speed of the generator has decreased, these fly balls also will be rotating at a speed below synchronous. As they are moving at a speed below synchronous, what is happening? The fly balls, they will be coming closer. There will be reduced tension on the spring. Fly balls will be coming closer, and as a result, since fly balls are coming closer, means they will be pushing B upward. Okay, they will be pushing B upward. As B is pushed upward, A remains fixed at its previous position. B cannot go up unless C also go up. So along with B, C also will move somewhat in the upward direction. D also will be moving somewhat in the upward direction. The opening created here will be reduced somewhat. So, and this process will go on as I discussed before. And when we discuss the oscillation of synchronous generator, when we have started discussing the active power control, then again there will be speed variation of the synchronous generator. Sometimes it is more than synchronous, sometimes it is less than synchronous, and finally a steady state will be established when the power output will become reduced than compared to the initial power output. So because of the power decrease command in this mechanism, the power output of the generator will be decreased. And when you give a power increase command, as we have discussed previously, during utilizing the same process, the power output will be increased by the generator. Okay, So this is how the speed governing mechanism actually functions. Basically, following a power increase or power decrease command, there will be some momentary change in the speed of the synchronous generator. That's why it is called the speed changer. Why it is called the speed changer? Because you are giving a power increase command or power decrease command. So for power increase or power decrease, the speed of the generator, it is a synchronous generator. Finally, it will be rotating at synchronous speed. But immediately following this command, the speed must deviate from synchronous speed. That's why you are giving either a power increase command or power decrease command. But as a result, speed of the generator will either increase or decrease, and this will be during the transition period also only. Finally, the generator again will be rotating at synchronous speed. Since this action, okay, this initiative basically is changing the speed of the generator momentarily. That's why it is called the speed changer. Okay, is it clear? Could you understand what is
Yes,
this
sir.
over? Okay. So now this is how the speed governing mechanism will work. And then we shall now see how the speed governing mechanism will be effective in controlling the frequency of the synchronous generator. And since you are controlling the frequency of a single generator, the same logic will be applied to all the generator, and this is how the frequency of the total system will be maintained. So we have to discuss all these things in greater details. What we shall do next, using this discussion, the functioning of the speed governing mechanism, we shall be developing a mathematical model of this function and then analyze and see how the frequency control may be actually implemented through this speed governing mechanism. Okay, so that we shall do in our next class. Any question you are having, you can ask me, or we shall conclude today at this point. Bolo.
Sir, in case of
Bolo.
active power, if we want to increase active power, then we shall to increase the delta angle. That means power angle. Sine delta it should be increased, and delta will be increased when the EF and VT angle between them will increase. And EF VT when they are synchronous, then previous they are at alpha, then synchronous. And if we increase the angle alpha, then we have to increase the speed of rotation of EF. So so speed of rotation of EF increase and the rotor speed will be increased. But why we are saying that the always the rotor will rotate will synchronous speed, then if rotate always rotate synchronous speed, how EF
No,
will
not always. It is synchronous speed at steady state, but during transient period, during dynamic condition, dynamic condition means some change in load, some increase in load, some decrease in load, some increase in input power, some decrease in output power. There, obviously, speed cannot be synchronous, because if the speed is synchronous at this frequency, then how delta will vary? Unless delta varies, you cannot change the power output of the
yes sir,
generator.
yes.
So to change the power output, the speed has to be changed, but that changes during the transition period only. That is not the steady state speed. Steady state speed for synchronous generator always has to be synchronous. Otherwise, the system cannot run. System cannot run at stable condition. Okay. Obviously, at steady state, the speed of the generator will be synchronous. But during transition, it has to be either above synchronous or below synchronous, depending upon the happening event that is taking place. Okay, is it
Yes.
clear? All right. Any other question? Anybody? Okay. If no question, let us now move to see who are present today. Okay. Now, Aditya Rai.
Yes, sir.